Welcome back to ECE 442-542. We are 1 week away from exam number 3. Homework number 6 is due on Monday, and the rest of the announcements pertain to exam number 3. I was told at the end of Monday's lecture that maybe we have this classroom on Monday at 7 o'clock. Is it okay if we stay here? We don't have to get up and move to the other room. That's where we will hold the review session. If you know someone that's not here, that's planning to go sit in the other room, you might remind them or tell them. I'll try to announce this again on Monday, but I think we'll just go ahead and stay put for the review session on Monday. If you have questions or topics you would like to see addressed in the review session, I've created a quiz on D2L. You can find it under the quiz tab, and it really is just you type in an answer or a line that says I want to see or I have a question on this particular topic. That should be self-explanatory. There is review material like in the past posted on D2L with practice exams, and again, last spring's exam will look more similar to this exam number 3 in terms of structure. The others, the material is shuffled a little bit, and you have to kind of look at just pieces and parts of previous exams to get the same kind of content for exam number 3 that will be this semester. Today what I want to do is look at the root locus approach, or what that is, with the example of constant or proportional control. And I'll do that by looking at, basically we will start out, how many, when you read, maybe not a novel, but a textbook, do you skip to the end of the chapter, or do you skip to the end of the book and read that before you even start so that you kind of know where you're going? Do you do that? I used to think that wasn't allowed. That's okay. You can go to the end and look at what you're expecting or maybe what's going to happen, and then when it's where you're reading, you go, oh, that's right, that's what we were supposed to be learning. I'm going to give you that with some examples. We're going to look at the end result to begin with, so that you don't just assume that they all progress in the same way in terms of sketching these root loci. How many have seen the root locus concept in the past? How many will admit to have seen it in the past? Okay, so it's not going to be a total repeat of something you've seen, I'm guessing, for everyone, but I hope that this time around maybe it makes even more sense. We will actually look at, if you can't get all of these rules or this concept down, I'll show you a way that you can just number crunch. You can plug in different values of k. That's really what you're doing. You're just looking at these roots of a closed loop polynomial as they vary with k. As you adjust k from 0 to infinity, how do the roots of that denominator polynomial change for different values of k? We'll look at a numerical example. I will then generalize the notation, meaning I will put all the poles and zeros from the controller and the plant together, and I'll just call that plant G bar, and then we can just isolate the gain K, and then all of these systems, whether they're systems with controller or just a system, look the same, and we just have to adjust the gain K, which is what we're doing in a root locus diagram. I then will allow you to read very quickly the rules. I'll read those aloud, and then we'll start going through some examples. But I wanted to collect those rules so that when you're trying to work homework problems on homework assignment 6, maybe you can say, oh, that's rule number, well, basically you can step through these rules. They may not all apply, but typically, and I think you'll only have to worry about the first 3 of the 50 rules for no, there's not 50, but there's a few. There's 5 or 6 rules, and you'll have to basically pay attention to the first three for exam number 3. That's why we're just doing 3, because it's, but these are the first 3 rules. This is the block diagram that we're playing with, a transfer function g and a gain k. We are simply adjusting the gain k. That's our adjustable knob from 0. We're keeping it non-negative. We're not allowing k to be negative. And now let's look at some possible root locus diagrams, and they are going to be sketched in red, the root locus. I think last time, didn't we cover this g of z equal to 1 over z minus 2? There, as you adjust the gain k, the closed loop pole in this closed loop transfer function just migrates from 2 all the way off to minus infinity. If you had a g of z that was 1 over z, z minus 2, and I've indicated the poles with blue x's, then you have a pole at the origin and a pole at 2. These 2 branches, there's actually 2 branches here, even though they're just all on one line segment. We will learn that as you increase k, the pole at the origin goes to the right, the pole at 2 goes to the left, and they meet between each other. If you don't have any other poles and zeros present, they meet halfway between. But if you have other poles and zeros there, they may not meet exactly in between, and we'll learn where they meet. Where they meet is called the breakaway point for obvious reasons. They break away from the real line. That will be rule number 3. We will be able to calculate that breakaway point, the value of z, where that happens. In this case, there's only 2 poles. They break away halfway between those 2 poles, and halfway between the origin and 2 is 1. They're going to go off they're going off to infinity. What's our pole 0 excess in that rightmost transfer function? 2. How many, what did I ask? How many poles? I'm asking, I forgot. 2. How many finite zeros? 0. What's the pole 0 excess? 2. How many zeros at infinity do you have? 2. So those branches in the root locus, you'll have as many branches going off to infinity as you have a pole 0 excess, or how many zeros you have at infinity. You have 2 zeros at infinity. Those 2 branches are going off to infinity. As you increase the gain k, their real part remains at 1, and their imaginary part are complex conjugates, and they just keep increasing as you increase the gain k. Unfortunately, that system will never be stable in the closed loop. We can't stabilize that system because the best we can do is both poles will be at 1. That's not good. And they will be there simultaneously, and then they will split, and they're always outside the unit circle. So we would have to introduce more than just a proportional gain to stabilize that system. Is that clear? These are the kinds of ideas and concepts I want you to start thinking about, and I wanted to sort of show all of these on the same screen. Now in the lower left-hand corner, we have a different g of z. We have a 0 right at the origin, and that's indicated by an open circle. All our finite zeros are open circles. We have 2 poles, one at 1, one at 2, and now we have a different configuration of this root locus diagram. What's the pole 0 excess? How many root locus branches do we have? We haven't really talked about that, but how many poles do we have? Open loop poles. How many closed loop poles do we have? Same number. We had 2 open loop poles, we have 2 closed loop poles, we have 2 branches of the root locus. They're going to start approaching each other. They're going to meet Maybe not exactly between, I didn't even calculate it, I just know they meet between somewhere. They go off, but in this case, because there's 2 poles on the right and a 0 in the center, once they break away, you can treat that as a radial distance and just draw a circle. If you didn't throw away your drafting compass, you can draw that circle. And then it just circles around and it re-enters that same radial distance on the left-hand side of that 0, and then one approaches the 0 as you crank up the gain. The other one goes off to the 0 at infinity. So you have one branch that goes off to infinity, the other one stays finite. Look at the next one in the lower right. How many poles do we have there? Open loop. How many x's? That's kind of a hard question, isn't it? There's 3. How many finite zeros do we have? 1. What's the pole 0 excess? 2. So now how many zeros at infinity do you have? 2, and so you would expect 2 branches to be going off to infinity, and in fact they do. But I'm trying to illustrate these different patterns because you can't get locked into thinking, oh, I have a 0, so they must circle around that 0. That's not necessarily the case. It depends on how these poles and zeros are located relative to each other, and we'll learn in rule number 2 a quick way of deciding. Last time we talked about the French bread, right, on the real axis. If we think of that real axis like a big loaf of French bread that's infinite in extent, goes from plus infinity to minus infinity, everywhere you have a pole or a 0 on the real line, you slice that French bread. And that gives you so many line segments, real axis line segments. But the root locus isn't on every one of those real axis line segments. I hope you can see that from these examples. In the upper left, we do have an infinite line segment that's a part of the root locus, but we also have an infinite segment that's not on the root locus. We have 2 line segments. And how many branches, root locus branches, do we have in the upper left? How many poles do we have? 1. So we have 1 root locus branch. We go over to the right, how many real axis line segments are there, or how many sections or pieces of this French loaf have we separated or identified? How many different pieces of that French bread do we have after they've been cut at the poles and zeros? 3 sections, don't we? We have a rightmost, we have a finite piece, and then an infinite piece on the left. But how many of those real line segments does the root locus live on? How many branches of the root? There's only 1 segment that the root locus lives on. How many branches of the root locus are there? 2. So that can confuse you sometimes the first time you're learning this. Wait a minute, I have 1 real axis line segment. I have 1 branch of the root. No, there's actually in that case 2 branches of the root locus. They come together on that same line segment. Is that clear? I'm distinguishing between line segments and branches of the root locus. And the other 2, you can see that we have different collections. Here's some examples that are somewhat similar to one of the problems on the homework. On the lower left, how many poles do we have? 2. How many root locus branches do we have? 2. 1 is finite, and it just goes from 3.5 into 1/2, and it gets stuck. It approaches that finite 0. The other branch begins at minus 1/2 and goes all the way off to minus infinity. That particular problem, you would have to check to see if it's even stabilizable. My guess is it may not be. Because as you're cranking up the gain to move that pole at 3/2 into the unit circle, you're also moving that pole that's in the unit circle possibly outside the unit circle. And if they move consistently, which they may not, your hope is that that pole at 3/2 moves quicker in distance than that pole at -1/2. But if the gain, as you're cranking up that knob, if you crank it up and you get to 1 on the right, and you've already zipped past -1 on the left, you can't stabilize that system with gain, with pure gain. Is this making any sense? Maybe I'm getting a little bit ahead of things for those that are just now seeing, because we're reading the last chapter of the book. But this gives you a feel, I hope, for where we're headed, what we need to be doing. And do you see that in the lower row of examples, the one on the right, look at how the realign or the root locus goes to the right, and the one on the left, on the rightmost section or branch of the root locus, it goes to the left. We start these root locus diagrams at the x's or at the open loop poles, and we terminate on finite zeros or infinite zeros with the branches. We're approaching infinite zeros or finite zeros with these root locus branches. Now maybe we can go back. We can start at the beginning. What determines the shape of these diagrams? And here's an example. I think we were just getting to this example last time on our lecture, where our plant now has a pole at the origin and a pole in the open loop. Where are the open loop poles in this system, capital G of Z? These are not difficult questions, but it's kind of late in the afternoon. We have one at the origin, I just told you that. Where's the other one? 3/2 or 1/2. Is this system open loop stable? No, because you have a pole outside the unit circle. And we can determine the behavior of that closed loop system from our cheer. That's kg over 1 plus kg. If you plug in the g and simplify, cancel the common denominators in the numerator and denominator, you now have your closed loop characteristic polynomial in the denominator, and that, as you adjust k, will influence your closed loop poles. The closed loop poles are what we're interested in, and the root locus is what results relative to all of those poles as we adjust k from 0 to infinity. At k equal to 0, what are the roots of that closed loop polynomial? 0 and 3/2. Those are our open loop poles at k equals 0. Now as we adjust k, we move k to bigger and bigger numbers, you'll get the root locus. Here I've tried to draw it or illustrate this numerically. I've created a table on the left, and I'm using this polynomial, z squared minus 3/2 z plus k. Is everyone comfortable with where that polynomial is coming from? That's the denominator of our closed loop transfer function. What I've done in the table is I've simply plugged in different values of k and looked at the roots of that second order polynomial. And you can calculate second order roots, I hope. Quadratic formula. If you plug in k equal 1/4, you get one of them approximately at 0.19 and the other one is at 1.31. And over here on the right, I've tried to indicate where those are with a square. We start at 3/2 and 0. Those are the x's. And then we start to approach each other. We go into each other. Is that making sense? Then we crank up the gain to 1/2. You're cranking in the root locus, you're varying k continuously. Here I'm looking at discrete values of k, just so you see how you can numerically do this. I know it's hard to believe, but when I was in your position, we still had programmable calculators, and I figured out how to program this into my calculator. He didn't say we couldn't. So on the exams, I would check my work by doing this numerically with the root locus. Just saying. So if you did that now, obviously the calculators have improved a little bit. I don't even want to tell you how long ago that was, but I'm just happy that we still had calculators then, barely. But we did. But if you had a TI Inspire, you could say, oh, let's use the complex zero function, because you don't know if this polynomial is going to give you real or complex roots. So I plugged in z squared minus 3/2 z plus k, and then I said, oh, give me a vertical line that says evaluate that polynomial when k is equal to something, and now I'm just going to iterate on k. I can just keep doing this formula over and over again. So I plugged in k equal 0.25, and I said, comma, the variable that I'm solving for is z, hit return, and I get the 0.19 and the 1.31 with k equal to 0.25. If you plug in k equal to 1/2, you get, now we've moved to z equal 1 and z equal 1/2. Is that clear? Can I continue to do this? If I now change this, what do I want to change it to? Actually, I sort of know what I want to change it to, but I've forgotten. Let's try 0.625. I can cheat, and I can go back. What do I want? 9/16. So that's not going to quite do it, is it? 9/16. What is this? Well, I'll just tell it 9/16. I told you it was late in the afternoon. So now what do I have? Now I have two poles right on top of each other at 0.75. That's what that's telling me. And if I go back to my notepad, that's now represented by that upside down red triangle in the chart and in the diagram. So my root locus is actually starting this way. This one's starting this way. They meet right there at 0.75, and then, as you can see, or if you can't, then you go back here and you go, okay, let me try this again, and now let me make that, doing it the hard way, but 3/4, or 0.75, and now I'm at 0.75 plus and minus j 0.33, or 433, and that's where my diamond is. I'm now moving up, and those, if I just kept increasing k, I just did one more, and that was the plus sign. I increase k to 1, and I get 0.75 plus and minus j 0.66. And that's now numerically validating this root locus diagram that I tried to illustrate before. Are there questions on that? You can now use your calculator to sketch the root locus if you want. And all you really have to do is know the quadratic formula, probably, especially for this one. Now, in general, you might have more roots than that, so it's nice if your calculator does something like complex zeros of a polynomial. Here's the generalized notation that I now want to go through. Uh-oh, now you're wanting to buy a new calculator, huh? Oh well. Just a few more weeks and you'll graduate, maybe. Not need that calculator. You can sketch these. You can learn this, how to do it by hand. Here is the notation that I want to hope that you buy into. We might have a plant, G of Z, which is now one of my poles is further out. It's at 2 and the other one's at the origin in my plant. And now I'm saying, well, why don't I put in a controller? You're going to have to learn how to design those capital C of Z's. And I've sprinkled one of my pole and zero. Actually, I pulled out the zero shaker and I put it right at the origin in my controller. I pulled out my pole shaker and I put a pole at Z equal to -1. You will learn how to do this based on your knowledge of the root locus diagram. But what I'm wanting to capture now is I'm going to push all of those poles and zeros into a common transfer function I will call G bar, and then I can isolate my gain K, and now I have the standard, if I use the proper feedback sign, now I have the standard block diagram for a root locus. And all I have to do is adjust the gain K to sketch the root locus for that combination of poles and zeros. Now, have I done anything illegal with that choice of pole and zero in my controller, capital C of Z? What have I actually done? I can simplify that capital G bar of Z, can't I? If you look at this, the G bar of Z, which I'm wanting to sketch the root locus for, has a 0 at the origin, and it has a pole at the origin. My plant started with a pole at the origin, and I'm saying, oh, I'm going to cancel that with a 0. I'm going to do a pole 0 cancellation. Is that valid? It's not unstable, is it? That pole and 0 cancellation is inside the unit circle. That's okay. I can't make those cancellations with anything outside. Or what do I have? I have an internally unstable system, potential. I will. You may not see it from the reference input to the output. It'll be oblivious to that cancellation, but another transfer function is going to not be acceptable. Here is now where I need your help. Here's the z-plane, and I want to sketch the root locus. I've indicated right now the poles of my original plant, the one at the origin and the one at 2. Now, do you remember what my controller was? What was my controller? I had a 0 at the origin and a pole at -1. So now I am going to introduce my controllers in green. I put a 0 right on top of that pole, and I introduced another pole at z equal to -1. Now I have my poles and zeros in my diagram. I want to now sketch my root locus. What does the root locus look like? And the first thing that I want to do is figure out with this French bread which piece of the real line is going to belong on my root locus, or are any pieces. Is the piece from 2 to infinity going to be a part of the root locus? You are now looking to say, if I was looking at a point out here, what's the angle that each of those poles and zeros make with that point? and their net angle needs to add up to minus 180 degrees. If I look from 2 to wherever, let's say 3, let's say that dot's at 4. If I look from 2 to 4 from that pole, what's the angle? 0, isn't it? The pole and 0 at the origin, they're canceling. One's upstairs, one's downstairs, so I'm not even going to worry about their angles. They're going to subtract away, but they are both 0 anyway. What about the pole at minus 1, the angle of that to that red dot? That's likewise 0, isn't it? So I have minus 0 gives me 0. I need the angle to be minus 180 to be on the root locus. Any point to the right of 2 is not on the root locus. What about any point between 2 and minus 1? Now I have, if I looked at this angle of that pole, that's 180. The angle from minus 1 to, let's say, 1/2 is 0. I have minus 180, minus 0, minus 180. Now every point between 2 and minus 1 belongs to the root locus. What about to the left of minus 1? I have the pole at 2. What angle is that going to contribute? I'm going to have to turn 180 degrees to get to something beyond minus 1. The minus 1, again, I'm going to have to turn 180 degrees to get there. I now have 0, minus 180, minus 180. Minus 360 is the same as 360. That's the same as 0. That's not minus 180. All points to the left of minus 1 are not on the root locus. Rule number 2 is easy to learn. Do we all know what even and odd are in terms of numbers? That's all we're doing with rule number 2 on root locus construction. We are standing on the real line, and we are asking this question. If I look to the right, are there an odd number of poles and zeros to my right? So if I am at 3, and I look to my right, are there an odd number of poles and zeros? These are finite poles and zeros to my right. No. What if I go to 1, or the origin, and I look to my right? Is there an odd number of poles and zeros to my right? Yes, so that segment, it belongs on the root locus. What if I go to minus 2? How many poles and zeros are to my right? You could say 2 or 4. Those are both, but what are those? 2 and 4 are both even. They're not odd, so anything to the left of minus 1 is not on the root locus. That's rule 2. How many branches of the root locus do I have in this example? 2, don't I? I have 2 poles. This one is going here, and this one is going there. And what do I know is happening with those 2? Do they just stay put? They come together. This is not peanut butter and chocolate. I'm hungry. I'm sorry. I'm thinking of Reese's. You got peanut butter in my chocolate. You got chocolate in my peanut butter. Now you have a pole at 2 and a pole at minus 1. One's peanut butter and one's chocolate. When they meet, they don't want to stay together. They leave the real line. They break away. Since I only have those 2 poles effectively, where are they going to meet? Halfway between those 2 poles, right? What's the total distance between that pole and 0 at the origin you can put on filters and just not even view them as being there because they're canceling each other. So if those are confusing you, you can mentally erase those because they're canceling each other. So now you're focused on two poles and only two poles. What's the distance between those two poles? What's the linear distance? 3. They're going to meet halfway between that distance. So the one at 2 is going to move 1.5. The one at -1 is going to move 1.5 to the right, and they're going to meet at 1/2. Right? Then what happens? Well, then we will learn what they do, but they're going to go off to infinity, because how many zeros at infinity do we have? The pole zero excess is 2. We have 2 zeros at infinity. That's our root locus diagram for that controlled system. Can we continue to crank up the gain k and remain stable? And if you say no, why not? We're going to exit the unit circle, aren't we? Can we crank up the gain to become stable? Or in the open loop, are we stable? No, because we're starting with a pole outside the unit circle at 2. We do have to crank up the gain k to become stable, but we can't crank it up too much or we go unstable. But we can stabilize this system with the controller that I picked out. And what's the lower limit on k to become stable? It's whatever gain is going to be necessary to get us to that point from that pole at 2, isn't it? We need to crank up the gain to get that pole at 2 shifted into 1. And we'll learn an equation for the gain k and evaluate that at z equal to 1 to find the gain k to get us to that point. Let's not do that right now. Let me just say, though, that the range for stability, do you see, I'm not sure I want to do this, but there's the unit circle. You know why I didn't want to do that, right? Because I can't draw a circle. Question? I know there's a circle tool, but I'm not going to be able to use it very well. And I won't be able to do a dashed with it. I'm not very quick with my sketching. Yes, thank you. I've tried to use it. I actually have them stored somewhere, but all my diagrams are different in size, and I'm terrible at placing the center of the circle and having it grow. But yes, thank you. That's a good suggestion. I wish I could use it. But I'm going to entertain you by drawing terrible circles. You can draw better circles. But now do you see where it's going to, where the maximum is? It's now, let's say, right there is the maximum, and I have the conjugate with it. And if we do this properly, I hope, we would find that this, for stability, we will find that after we learn some more tools. But let's just move on. Is it clear, though, what we've done so far? How we were able to sketch that rather quickly, that root locus, to tell us where all the closed loop poles are possible, with the gain k being adjusted from 0 to infinity. And we can't stabilize the system, or the system is not stable in the open loop. We have to crank up the gain to at least 2. But we don't want to crank it up beyond 3, or we'll go back unstable. There's a limited range for stability. Just as a reminder, all of these root locus rules that we are going to now discuss, I'm just going to present, and then we're going to use them with some examples. And then you can go back and read them and study them and ingest them. And we've already talked about Rule 2. And Rule 1, we already know where the root loci start and stop, or begin and end. So you already know the first two, and we'll just quickly read through those, but they all come from the denominator polynomial in the standard configuration. 1 plus k g bar of z equal to 0. And because we can now solve that expression for kg bar, that becomes equal to minus 1, but minus 1 as a complex number has a magnitude of 1 and an angle of minus 180. And that gives rise to these two conditions. We have the magnitude condition. That's true on the root locus. And the root locus is the locus of points of all possible closed loop poles. And we have the phase angle condition. The angle of all of those poles, finite poles and zeros, need to sum to minus 180 if that point is going to belong to the root locus. Which means I could give you a now I'm going to upset you probably, but you don't know what's beyond this line, so I guess it doesn't matter. You haven't seen that next set of text. But what you could do, I could, on an exam, I could give you a pole zero pattern, and I could ask you, is this point right there on the root locus? That could be a question. And how could you determine whether that star was on the root locus or not? If that point is on the root locus, what do you know has to be true at that star location? The angles, all of those angles, need to sum up to minus 180 degrees. Which means if you had your protractor with you at the exam, hint, hint, you might want to bring your protractor. You could measure this angle. Let's say that's theta P1. You could measure this angle, and that angle is relative to this horizontal line, and let's call that theta P2. This is getting really busy. But this angle now to that star, let's say, is theta P3. This is now a 0 angle, and it's measured relative to this horizontal line. This is theta, let's just call it Z, since I don't have more than one Z. And this pole has an angle to that star, and that's theta sub P sub 4. And the phase angle condition says that the net sum of those angles need to equal minus 180. You could measure all of those angles, and you would now be saying, oh, I have theta sub Z minus all of these poles, angles, which are theta P1, theta P2, theta P3, plus theta P4. And now you're saying, is that equal to minus 180? If the answer is no, then star, that point star, is not on the root locus. If the answer is yes, if all of those angles net out to give you a value of minus 180, then star is on the root locus. Are we clear with that? You could then validate a root locus diagram by checking each point. You don't want to do this, but if I just gave you one point, that's doable. You wouldn't want to do it for an infinite number of points, but you could check 1 or 2 points fairly easily, maybe, if you didn't have too many poles and zeros. But now that discussion was hopefully aimed at you learning how to compute angles from poles and zeros, if you didn't already know. We did it for angles relative to the real line before, but we can do angles anywhere in the z-plane from poles and zeros. And the poles are in the basement, that's why we're subtracting them in this transfer function, let's say g bar. And the zero angles are in the numerator, that's why we're adding those. Questions on that? Hypothetical question. Let's now look at these root locus construction rules. Like I said, don't worry about writing this down. Just read it and digest it. Since you've already had some peanut butter and chocolate, we need to digest that. Rule number 1 is really just telling us where the root locus starts and where it stops. The root locus branches begin on the open loop poles of g bar. Those are the roots of d of z. And the branches end on the open loop finite zeros of g bar. Then in green is just some added information. The finite zeros of g bar are the roots of n of z, that's the numerator, accounting for the factors from the controller and the plant. Those are both contained in n of z. The number of infinite zeros of g bar, which equals the pole zero excess, determines the number of branches of your root locus that go off to infinity. That's all we've been saying all along. That's rule number 1. That's almost a trivial rule. You just sketch your, or find your transfer function and plot your x's and o's. The hard part is going to be later when you have to sprinkle poles and zeros to try to stabilize a system. But we're not going there yet. You just now need to learn the rules. Rule number 2. Assuming a non-negative gain, k, this now just tells us which of these line segments on the real line belong to the root locus. Real axis segments in the z-plane, those real axis segments are defined by where your poles and zeros are. Those are slicing up your real line into segments. Real axis segments in the z-plane belong to the root locus if an odd number of poles and zeros lie to the right of the line segment. That's what I tried to say before. And points on the line segment satisfy the phase angle condition. That's the verification or the validation of rule number 2. You can test it by just applying the phase angle condition. Those points need to have an angle of minus 180. That's rule 2. Those are easy. Rule 3 is a little more interesting, and we will learn how to use that in a minute, but let me just state it because I may not be able to write it quick enough near the end of class. Here is rule number 3, and this applies when more than one branch of the root locus lies on the same real axis line segment. Is that too wordy, or is that making sense? You now have 2 poles, and they are joined by a real line segment, but there's actually 2 branches of the root locus on that one line segment. They can't just get stuck on the real line. They have to go somewhere. They don't always go straight up and down, and we'll learn that later. But they do break away. Where do they break away? Well, remember what's happening. Where are the poles at k equals 0 in that sketch that I've indicated? Where are they relative to those blue x's when k is equal to 0? It's not a trick question, but it's a trivial question. They're right on the x's, aren't they, at k equals 0. Now, as we crank up the gain k, the one on the right, it starts moving to the left. The one on the left, the pole on the left, starts moving to the right as we crank up the gain k. What happens when they meet? Can you see that along that line segment, k is increasing, 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 and right when they meet, that's the biggest k is going to be on that line segment. That's going to be a relative maximum of k. A relative maximum. A maximum. Now you know why you learned your calculus. Now we can do maximization problems, and if we wanted to, we're going to find the formula for k, and we can take the derivative of that with respect to z and set it equal to 0, and that will allow us to find the maximum value, or the location where the maximum occurs between those two poles. And that's going to be valid when we have a bunch of poles and zeros. We'll have a formula and we'll differentiate. That's kind of ugly, so we'll learn how to do it numerically also. But do you understand that they are going to meet, and that's called the breakaway point, where they meet, where k is a relative maximum. That's as big as you can crank up k and still be on the real line. You crank up k beyond that and they split off. They break away from the real line. The opposite scenario is if we had two zeros and a real line, a root locus segment between those zeros. Then the branches are going to come into that line segment. They're going to meet, and then they're going to go off to the zeros. That's a re-entry point, not a breakaway, but a re-entry point. And that's a relative minimum value of k. This will make more sense as we play with some examples. But that's rule number 3, breakaway and re-entry. And we don't have to have those in pairs. We could have breakaways and no re-entry. We could have re-entry and no breakaway. Or we could have breakaway and re-entry. We've seen those already. If we go back to the examples somewhere, if we look at the lower left-hand picture, and on the exam I said, where is a breakaway going to occur? Could you tell me a region on the real line where a breakaway is going to occur on the lower left picture? And you can be very general. You could define that segment or bound it by poles and zeros. And I might say circle. I wouldn't have the root locus sketched, and I might say circle the line segment where a breakaway occurs. And I might say box the region, the real line segment, box that where a re-entry occurs. Do you see that you have a breakaway and a re-entry in the lower left picture? The breakaway is between 1 and 2. You could sort of do an oblong circle there. And you could box a point or a region that's to the left of that 0 and say, oh, the re-entry is over here. Without even sketching the root locus, you know you have a breakaway and a re-entry. What about on the right? What do you have? Do you have a breakaway? Yes. Do you have a re-entry? No, there's no branches coming back into the real line. Is that clear? That you could have one or the other or both? Rule 3. Okay, all right, now I'll slow down. And, well, I shouldn't. Let's go fast through this. Let's revisit example number 2. Here is G of Z, or G bar of Z. It's going to be, I will play both many different, well, you'll just have to know what I'm meaning. Let's start to sketch the root locus for this. And you already know what it looks like, I hope. What's the first thing that you probably want to ask when you're sketching this root locus? I might ask the number of root locus branches. How many closed loop poles am I going to have if I put this in the generic unity negative output feedback configuration? How many closed loop poles am I going to have? 2, aren't I? So I have that many branches of the root locus. I started with 2 poles. One is at the origin and one is at 1.5. Those are my starting points for the root locus. I've basically captured rule number 1. Let's use rule number 2 and determine which line segments belong on the root locus. And you could now just look. How many pieces of the French bread do you have? How many line segments are identified with this pole 0 pattern? If you have an infinitely long piece of French bread, how many places is it getting cut? You're getting it cut at 3/2 and at the origin, so you're separating it into 3 line segments. You have 3 line segments. Are any of those line segments on the root locus? Is the segment from 3/2 to infinity on the root locus? No. If I go here, how many poles and zeros are to the right of 3/2? 1, which is odd, so this belongs, that one's going here and that one's going there, and there's line segment between the origin and minus infinity is not on the root locus. Just from this picture, can we talk about the lower limit of stability? Or is the open loop system stable? Do you see what well, we've already talked about the breakaway, haven't we? Rule 3. You know where the breakaway is going to occur. It's going to occur, I hope you realize that's going to occur to the left of z = 1. What's the distance between those 2 poles? What's the length of that real axis segment that is a part of the root locus? 1.5. And there's only 2 poles. You're going to split that right in half, and that's where they're going to meet and break away. You know they are going to break away halfway between each other. That's going to be half of 1.5, or 3/4. That's going to be at 0.75. It's where they are going to break away. Oops. And they're going to go off to infinity. The lower limit on stability is going to be when we crank up the gain k to get to that point. Is that clear? We want to know what is the gain k when z is equal to 1. So let's look at developing the formula from first principles. We know that the denominator of our closed loop transfer function is governing stability, and that's 1 plus k g of z is equal to 0. In our case, we have 1 plus k, and our g of z was 1 over z minus 3 halves. That's equal to 0. When that equals 0 is really, well, we can solve that and say, oh, we're interested in k, z minus 3 halves equal minus 1. Or that's 1 at minus 180 degrees. And our magnitude condition allows us to say that the magnitude of k, z minus 3 halves, must equal 1. And we are going to assume that k is non-negative. So the quotient of the magnitude is equal to the the quotient's magnitude is equal to the quotient of the magnitudes. So I can look at the magnitude of the denominator divided into the magnitude of the numerator. But the magnitude of the numerator I'm assuming is positive, so I'm going to just forget that and solve this and say that I can now, from this, say I have k, z minus 3 halves is equal to 1. Are we okay with that? Now, the product of the magnitude of the product is equal to the product of the magnitudes. Meaning I can now say that I can solve this for k, and k is now equal to the magnitude of z and the magnitude of this other factor, z minus 3 halves. Just solving that for k. And now I have a formula for k. And I can evaluate that along that line segment that I know the real or the root locus belongs to, and I can evaluate or find the k at any point along that line segment. The point I'm interested in for the lower limit of stability is when z is equal to 1. That's how much I have to crank up k in order to get the system to become stable, to move it inside the unit circle. And I'll indicate that by saying k with z is equal to 1 is now z and z minus 3 halves with z equal to 1. So that's 1, and this is 1/2, or k equaling 1/2 is going to give me a pole right at z equal to 1. The other one is coming towards that. Yes, question? So now the question is, how do we know that the pole starting at the origin isn't moving much faster? And that's a great question, because you don't want to assume that in general these poles are approaching each other at the same rate, meaning one might be going further in distance than the other one. But when they are just two in isolation, they are going to approach each other consistently. And we know that they eventually will end up at 0.75 at the same time. By same time, I'm meaning for the same value of k. So we know that, or from that, then we can conclude that it's going to require a gain k to get that pole at 3/2 to 1 before anything else is going to happen. So that pole at the origin is not going to zip up and start going up an upper branch. They're going to meet at the same value of gain k and break away together. Is that clear? But in general, if you have more poles than zeros, the one from the right may approach more slowly than the one on the left, or vice versa. You don't know necessarily. You can determine. But now let's determine what is going to happen, or what are the closed loop poles when k is equal to 1/2. We found that one of them better be at 1. So now what are the closed loop poles when k is equal to 1/2? Well, we know what the formula is. That's this 1 plus k g of z equal to 0. We have 1 plus k z minus 3/2 equals 0, and we're really just interested in the numerator of that expression. That's when the whole thing will vanish. So if I put that over a denominator, the numerator is going to be z minus 3/2 plus k. And I want to know what happens to those two roots when k is 1/2. Or I now have z squared minus 3/2 z plus 1/2 equaling 0. Now I can cheat because I already know that one of those is at 1. So I can factor that. I can say z minus 1 is a factor of that. And if that's the case, I hope it's clear that I can now identify the other factor, because it has to be such that I produce that quadratic expression when I multiply it by the z minus 1. And the product of the two constants needs to be plus 1/2, and their sum needs to be minus 3/2. This now says that z is equal to 1 and z is equal to 1/2, so they have moved the same distance for that value of gain k. And these are the closed loop poles. Since one started at the origin, moved 1/2 to get to 1/2, one started at 3/2, it moved 1/2 to get to 1. These are the closed loop poles of your system when k is equal to 1/2. Now we can answer some more questions. We can say, what happens let's say, what happens to the closed loop poles which is really just what's happening to our root locus, and we've already told ourselves what that's going to be as k continues to increase. We know that we have z minus, or z times the quantity z minus 3/2 plus k. That's our polynomial of the closed loop. This is now z squared minus 3/2 z plus k. And we can now ask, is there a maximum value of that gain k when the roots of that quadratic are still real? And we know the formula for k. That was this formula right here. K is z times z minus 3/2. we can now use that. We know that K is Z times Z minus 3/2, or it's Z squared minus 3/2 Z. And we know we need it to be positive because we're having a non-negative value for K. So we can now find the maximum of that by taking the derivative of that expression for K with respect to Z. This is now 2Z minus 3/2, and set that equal to 0. Z is now 3/4. Solving that, we found the relative maximum on that real line segment. We can now evaluate the K expression at that relative maximum to find out what K needs to be to crank it up to that point. And now we have 3/4, and 3/4 minus 3/2 is a negative 3/4, which we're going to take the absolute value. And now we have 9/16. And this is the relative max of K. And that's really rule number 3. That's the relative max, and we now know the value of gain K to get us to that relative max and what that's going to produce. So you could evaluate the second order polynomial when K is equal to 9/16 and factor it, and you'll get the right answer. You'll get your poles at 3/4. What happens as K increases beyond 9/16? What do we know is true about the root locus? We had a pole here and a pole at 3/2. We know that they are approaching each other and they meet halfway. But if I said, oh, is this point on the root locus, what would you tell me? I don't know, let me calculate. So now you calculate and you say, oh, this, what's the angle there? Roughly 90 degrees. What's this angle? 45 roughly. So now we have minus 90, minus 45, minus 135. Is star on the root locus? No. Is it clear what I was trying to do before I erased it? I've been sketching this for 2 poles as 2 branches of the root locus that go off at plus and minus 90 degrees. Why is that true? Can we verify that? Let's now look at what happens for a point right there. Let's call this angle theta P1, and this angle theta P sub 2. We now can say, oh, we better have minus theta P1 plus theta P sub 2. Well, I can sort of, well, do you see how theta P2 and theta P1 are related? They're supplementary angles. Am I using the right phrase? They sum to 180. So theta sub P2 is actually 180 degrees minus theta P1. So that now if we looked at this, we now have minus theta P1 plus 180 degrees minus theta P1. That's minus 180 degrees. Yay! That's what we wanted, wasn't it? And that's true for any location on that vertical line halfway between those two poles. That's a verification of why I was able to sketch the root locus as quickly as I was when I just had two poles and nothing else around. Now, what's the upper limit on ability? Do you see that there is an upper limit? Why am I sliding around? You could sketch the unit circle. You know the real part. What's the radius of the unit circle? 1. So now you have a radius of 1 is the real part squared plus the imaginary part squared. You can solve for that imaginary part, and you know now the z location where you intersect the unit circle. You can use that z value, even though it's complex, you can plug it into this k and find the k to get you to that point. And you'll find, I hope, that that's 3. It was 2 to get us to 1, and then we keep cranking, and you'll see that it's 3 to get you to 3. Well, maybe I'm off. I'm having too many examples, but you can calculate. You see how to calculate the z value and then the gain to get you to the unit circle? And if you cranked up the gain k more than that, you would be unstable. Whew. So we'll pick up at that point on Monday.